Hello students, today we're going into curve sketching, a very important topic in calculus. So we are going to be using the theories that we have learned on first and second derivative to help us to draw some pretty graphs. We will be using our graphics calculator at the later part of the lesson, but we should be able to draw a lot of the graphs even without the graphics calculator. Again, very important topic. You might want to spend a bit more time on this topic. And yeah, let's get into it. So what are we doing today? The learning objective of the WOLT. Today we are going to cover the fourth and the fifth dot point. You want to understand and use the second derivative test to find local maxima and minima. You haven't heard these terms before. We're going to explain what they are. And also we're going to be sketching some graphs, the graph of a function using first and second derivative to locate secondary points and points of inflection. It sounds super complicated, but I'm going to use a few different examples to illustrate how it is done. Very important topic today. Alright, by now you should be familiar with these general shapes. If you've got a curve that looks like this, you should be able to infer that it would be a quadratic function or a degree 2 or a second order polynomial function. If a curve looks like this or looks like this, cubic, degree 3 or third order polynomial. And sometimes we haven't really spent a lot of time with the fourth degree functions, but if it looks like this, then that would be a quartic function or a degree 4 or a fourth order polynomial function. But you need to be very familiar with these two already. Now I'm going to go through some very important definitions. A stationary point on a curve is defined as a point where the gradient is 0. Alright, a gradient as a 0, we call that point a stationary point. If you know the gradient is 0, we can say dy dx or f dash x would be 0. Very important definition. You must know this. Stationary point is where the gradient is 0. There are three types of stationary points you should be familiar. One is called the local maximum turning point. One is called the local minimum turning point. And then you have the horizontal or the stationary point of inflection. Why do we use the word local? It's because sometimes in other textbooks you will see it's called relative maximum turning point or relative minimum turning point. It's because a point is maximum or minimum in a particular locality or neighborhood. I'll just draw you a picture to show you what I mean. So if I've got a curve that looks like this, if I've got a alright, so this we would call it the local maximum turning point. Well, because this is the maximum point at this vicinity, right? The graph I know is going to, well, if the graph looks like this, this point onwards would be higher than this one. So this is not the absolute maximum point, but we call this the local maximum turning point. Likewise, this point we'll call this the local minimum turning point because this is the minimum point at in a particular locality or neighborhood, right? Around this area, this is the minimum point. So we call this the local minimum turning point. We call it the turning point because, well, the curve would be decreasing, and then up to this point it becomes increasing. So this is the minimum turning point because it is the smallest point around this area. And if you look at this point, we call it the maximum turning point because it was increasing. But when we get to this point, then it becomes it's decreasing, right? So this is the maximum turning point, but it's a local maximum turning point because it's not the absolute maximum turning point. As you can see, the graph keeps going up. So we would have lots of points that are bigger than this one, but around this area, this is the maximum point. And then if we have what is a stationary point of inflection, if you've got a graph, and then, right, I should draw it better. So at this point, the gradient is 0, but the concavity of the graph changed. I'm going to show you some better pictures. My drawing's not really great on this writing pad, but you will see a better picture of what the stationary point of inflection means. All right, moving on. Okay, so this is a very important summary table. Very, very important. Let's look at it one by one. If we look at, we've got a curve that looks like this. At this point, it is called the maximum turning point, right? It is a maximum turning point because there's no point greater than this one. All right. At this point, you can see the gradient as 0. So if you look at the first derivative, dy dx is equal to 0. The gradient is at 0. What about the second derivative? When we look at the second derivative tells us what? Well, the second derivative actually tells us the concavity of the curve, right? So if I've got a second derivative, if you don't remember that, you will need to go back to the lesson before, right? The second derivative tells us whether or not the curve is concaving up or concaving down. If we've got a second derivative that's less than 0, then we can say this is a curve that's concave down, right? Now let's look at a minimum turning point, the second one, the minimum turning point. At this point, it is the smallest point around the area, right? The curve is decreasing, decreasing, decreasing up to this point, and then it increases again. It changes the direction. That's why they call this the turning point. Again, the first derivative tells us the gradient at this point is at 0. Second derivative tells us the concavity. If the second derivative is a positive number, if it's greater than 0, we can say that it concave up. Now we look at the second stationary point of inflection. All right, the tangent is horizontal. If we look at the gradient at this point, it is at 0. Right, the gradient is 0. So what does the point of inflection mean? It means concavity changes at this point, right? So stationary point of inflection is where the concavity changes. So this curve changed from concaving down, then it's concaving up. At this point, the gradient is at 0. And what about the second derivative? The second derivative at the point of inflection would be 0. But that's not enough. You still need to check the sign at either side. So we need to find a number that is slightly smaller than that point. And we check, oh, okay, before this is concaving down, we should have negative second derivative. And then after this point, so this bit represents this bit, the bit before the point, you should get a negative second derivative, and this bit represents the bit after the point. Yes, it will get a positive second derivative, and this bit obviously would be the point of inflection. So if you can to verify whether or not a point is a stationary point of inflection, you need to use the second derivative test. First, is the second derivative equals to 0? Does it equal to 0? Then you need to check whether or not the signs change at on the left and then to the right of the point. Just for completeness sake, we are going to talk about non-stationary point of inflection. So this is not a stationary point, but it is still a point of inflection. Well, at this point, it is not a horizontal tangent. Right? At this point, the gradient is not 0. So you will see the first derivative does not equal to 0 because at this point I don't have a 0 gradient. Compare this one to this one. This one has got 0 gradients, but this one, no, it's actually a slope. So the first derivative does not equal to 0. However, if we look at the second derivative again, you need to remember, second derivative deals with concavity. At this point, concavity actually changed. This was concaving up before, then it becomes concaving down. So, and at this point, you would find second derivative equals to 0 because concavity changes at this point, and you do the check, positive concavity, the positive second derivative, and a negative second derivative. So this is actually a point of inflection, but we can't say it is a stationary point of inflection because the first derivative does not equal to 0. However, for this course, we are going to be focusing on these three. Alright, so I'm not going to spend too much time on this one. I just want to talk about the top three. Maximum turning point, minimum turning point, and stationary point of inflection. So these three, I just put it there so then it's complete, because you know there are also non-stationary point of inflection, but for the focus of this course, we will focus on the top three. Just to reiterate what we talk about, the first derivative tells us the function, the first derivative of the function gives us the gradient of at any point. Very easy to understand. You should know this to death by now. Right, the first derivative gives us a gradient of any point. So if dy dx is greater than 0, we know the function would be increasing. Right? If we know that the y dx is positive, well, we know that it's going to be increasing. So this represents this first case. Dy dx less than 0, we know the function is decreasing. It is sloping down, right? It's sloping down. So this is talking about this case, right? Sloping down. But if dy dx equals to 0, then we are at a stationary point. Okay? Stationary point is when dy dx equal to 0. You must remember this. Now let's look at what the second derivative tells us. The second derivative gives us concavity. I know I'm repeating myself a few times, but then you should know if I'm repeating myself, it is a very important concept. Second derivative of a function gives us the concavity of the curve. If we have d2y dx square, or the second derivative, or y double dash, is greater than 0 or positive, then we know the function is concave up. So it's this guy. If the second derivative is less than 0, we know it is concave down. And the last one is the interesting one. If it equals to 0, second derivative equals 0, and changes sign, then there is a point of inflection. So the important bit is you must check if it changes sign. Don't just assume that I've got d2y dx square equal to 0. It must be a point of inflection. Well, it might not be. Alright, so let me just put a note there. Please must check sign change. Alright, so you can see this is a point of inflection. This is also a point of inflection, although the gradient is at this point is not 0. So this is a non-stationary point of inflection, and this guy would be a stationary point of inflection. All right, very important slide. Okay, I'm going to give you a little job to do. I want you to investigate this curve. Y equals to x to the power 4. Take away 4 times x cubed plus 10. I want you to graph this function. What I want you to do is, I want you to first, well, you can use your graphics calculator, but you're going to graph this function. Then underneath this function, I want you to graph the first derivative of this curve, and then underneath the second curve, I want you to have the second derivative. So what I want is, I want you to give me 3 curves. The first one is y, and then on underneath it, then I've got y dash, and then one underneath this, I've got y dash dash. All right, and I want you to line these 3 graphs up. Then what you're going to do is you're going to identify the point of inflection, and then you're going to identify some maybe minimum or maximum turning points, or local maximum minimum turning points, and then you're going to look at what it looks like with the corresponding x values on the y dash curve, and also the corresponding value of the y double dash curve. All right, so have a go at it. Pause the video first and have a go. All right, so let's look at what you should have got. All right, you have the original function, this guy. Then you would differentiate this and get this, and then you plot it below it, and then you differentiate again and you get the bottom one. And then you're going to, sorry, I should have the laser pointer. So this is the original function. You should have plotted. Then you differentiate it, and then you plot it below. Then you differentiate it again, and then you plot it below. Now I want to look at the different points, or the important points of this curve. The first, well, you know this curve has got an order of 4, or the quadratic function. This is the first key point, right? You can see the concavity will change at this point. Stationary point of inflection. How do I know it's a stationary point of inflection? Well, because if I look at the corresponding point on the first derivative function, right, it is at 0. So the gradient at this point is 0. And how do I know it is a point of inflection? Well, because I know at this point, the second derivative is 0, but a little bit less than it, we have positive second derivative, and then a little bit right of it, we have negative second derivative, right? So the sign change at this point. If it was positive before and then it became negative, so the concavity has changed. How do I know? Well, looking at this curve, you can see the concavity has changed. It was concaving up, then now it's concaving down. But the second derivative also proves this fact, because before this point, you can see we've got positive second derivative, and then we've got negative second derivative after that point. All right, so let's look at another point. Here, we've got another point of inflection. It might be hard to see on this curve, but then we can infer it if we go backwards, right? If we look at the second derivative function, you can see, all right, here I've got a point at 0. I've got second derivative as 0 here. And then I know the sign has changed at this point. On the left of it is negative, on the right of it is positive. So this point at x equals to 2, it must be a point of inflection. So if I look at this point, well, you can see that it is concaving down, and then after this point, the curve is concaving up, right? It is a point of inflection. But is this a stationary point of inflection? Let's have a look. Let's look at the second derivative. Well, it's not, because the second derivative is not at 0, right? It is at it is negative, And you can also infer it has to be negative, because you can see if you draw a tangent on this line, it is negative. It is not at 0. So it is a point of inflection, but it is non-stationary point of inflection. The concavity change at this point, but the gradient is not 0. Now look at another point. We'll look at this point. Looking at here, you can infer that this must be a local minimum turning point. We don't have another point smaller than this, right? It is a turning point, and it is a stationary point because the gradient is sitting at 0. So you look at the first derivative function, you can see it is sitting at 0. And well, you don't really need to look at the second derivative. Well, the second derivative tells us whether or not it is concaving up or down. So if you look at it, it's a positive second derivative, so we know that it is concaving up, right? So that's how you link these three together, right? You can use the first derivative function to find the gradient at any point of your curve, and you use a second derivative function to identify the points of inflection, to identify the concavity at different parts of the curve. So here I've listed some key considerations that you should think about when you are sketching a graph. All right, very simple. The first one is common sense. You need to always indicate where the y-intercept is. So obviously you sub in x equals to 0 to find the y-intercept. Also, you might want to indicate where the x-intercepts are. You solve for you set y or f of x is equal to 0, and then you solve for x to determine where the x-intercepts are. Sometimes I put a note, if possible. It might not be possible because you might have a graph that doesn't cross the x-axis. Next, you want to determine the coordinates of stationary points and the natures. All right, so you need to determine where are the maximum and the minimum turning point. Do I have any points of inflection, and the nature? What type of turning points are they? Okay, so actually I also said points of inflection. Consider the restriction of the domain. Okay, so consider the restrictions on the domain. Are there any restrictions on the x values of your function? And then calculate the coordinates of the endpoints of the domain where appropriate. So if there are restrictions on the x values, you might want to find the coordinate of the biggest number and the smallest number for x. Then also identify vertical and horizontal asymptotes. Sometimes when you have a function, there might be asymptotes. You need to identify where they are. So the line or the point that your curve will never be able to cross that line, or they'll never be able to touch that line, asymptotes. And also you need to consider the direction of the f of x as x approaches positive or negative infinity. So when you are sketching a graph, let me just bring up the pen. When you're sketching a graph, you want to know whether or not, well, is the graph, if this is x, right? So as x approaches infinity, as x become bigger and bigger, is your graph going to go up or is your graph going to go down? And same as x approaches negative infinity, is the graph going to go up or is the graph going to go down? So you're just going to sub in a really big number or sub in a really small number so that you know which direction is your curve going. So these are just some tips on how to sketch a function. You might not need to use all of these. I just listed a few things that you might need to consider, you might want to consider. And I think it's more worthwhile for me to actually go through a few examples to show you how this process is done. Okay, so let's look at a very important example. I need you to really pay attention at this example, because sketching a function is very important and you need to know what is involved. It takes a while to finish this question. It would be, if it's an exam, it would be a big question because it can test you on a lot of concepts. So I want you to really pay attention at this example. So the question is asking you to sketch the function, this function x cubed plus x squared plus 9x, by determining the coordinates of all axis intercepts, meaning x-intercepts, y-intercepts, as well as any stationary points and the nature. So it's asking for what are the stationary points, the maximum or the minimum turning point. All right, and what sort of turning point? Is it a max or is it a min? And also include on your sketch the coordinates of any points of inflection. So it wants to know whether or not we have a point on this graph, the concavity would change. So have a look. Think of what strategy would you use. Maybe pause this video for a while. Really think about how you can tackle this problem, and then we're going to work on this together. Alright, so let's go through this together. Let's do the easy parts first, okay? Just get the easy marks first. Y-intercepts, always the easiest to find. Well, that happens when x equals to 0. If x equals to 0, then we know f of 0 would be 0 because just subbing into the original equation, 0 plus 0 plus 0 equals 0. So y-intercept is at 0, 0. Let's work out the x-intercepts. X-intercepts happens when y equals to 0. So 0 equals to x cubed plus 6x squared plus 9x. So we're going to solve for x. How can we solve for this? Let's look at these three terms. Do I have any common factors that I can take out so I can factorize and make it to a more solvable form? Well, I can take the x out, and that becomes x squared plus 6x plus 9 equals to 0. That's just a quadratic equation inside a bracket. I can factorize it even further. That becomes x plus 3 squared equals to 0. So now if I solve for x equals to 0 or -3. So x-intercept happens at 0, 0 or 0 and -3. Okay, so let's look at what we can do to, sorry, I just wrote the wrong thing here. I just realized it should be x-intercept. Sorry, I was being silly. -3, 0. All right. Okay, so next I want to move on to finding the stationary points. Okay, let's find the stationary points. What do we need to find? What do we need to use to find the stationary point? Well, we need the first derivative, and we also need the second derivative. The first derivative will help me to find, okay, where are the points when the gradient is equal to 0, and the second derivative will tell me the concavity. All right, what sort of stationary points are they? All right, so let's have a look at this. So we know f of x is the original equation, so f dash x. So let's differentiate that. Becomes 3x squared plus 12x plus 9. So that is the first derivative. And we also need to find the second derivative, f double dash x equals to 6x plus 12. All right, so we will be using these to help us out. We know at stationary points, the first derivative has equal to 0, right? The gradient equals to 0. So let's solve for x when f dash equals to 0. So we're going to make 3x squared plus 12x plus 9 equal to 0. And now I want to solve for x. I can take the 3 out. X squared plus 4x plus 3 equals to 0. If I factorize it, I will get 3, x plus 3, x plus 1 equal to 0. Therefore, x equals to negative 3 and x equals to negative 1 would be the stationary point. So the stationary points are at these 2 points. Alright, so let's see what else can we do. What we want to do is, well, we have found these 2 points. We need to sub that into the second derivative to see whether or not it is concaving up or concaving down. So we're going to get f double dash negative 3. Right, we're going to sub that into the second derivative, this guy. Okay, so 6 times negative 3 plus 12, negative 18 plus 12, we got negative 6. We know negative 6 is less than 0, which means it is going to be concaving down at this point, or it's going to be a maximum turning point. We'll do one more, f double dash negative 1. 6 times negative 1 plus 12. We're going to have 6 is the answer, greater than 0. Well, if the second derivative is greater than 0, if it's a positive number, we know it's going to be concaving up or minimum turning point. We're going to continue on the next slide. Alright, so let's write it out nicely because communication is very important to show the marker that you understand the concept. Alright, from the previous page you have found at x equals to negative 3, it was a turning point. But how do we know what sort of turning point it was? We use the second derivative, right? Not it was concaving up or down. So we saw at x f double dash of negative 3, it worked out to be negative 6, which was less than 0. If it was less than 0, it means it is concaving down, right? Concaving down, which means it looks like that, which means it would be a maximum turning point. But have we done enough? No, we have not, because we need to know what's the y coordinate at x equals to negative 3. So we need to sub in f negative 3. We need to sub in x equals to negative 3 into the original equation. So it will be negative 3 cube plus 6 times negative 3 square plus 9 times negative 3, and it will be a calculator exercise. It should work out to be 0. So therefore, maximum turning point at negative 3 and 0. Likewise, you do the same thing at the other turning point at x equals to negative 1. F double dash negative 1, we found it to be greater than 0, which means it's concaving up. Alright, it's concaving up. So it has to be a minimum turning point. We also need to find the y coordinate of this guy. So we sub in negative 1 into the original equation. It equals to negative 1 cube plus 6 negative 1 square plus 9 times negative 1. It will be a calculator exercise. You should find at the minimum turning point that should work out to be negative 4. Therefore, minimum turning point at negative 1 and negative 4. Alright, so we have done this bit of the question now, stationary point and the nature. The question also asks for points of inflection. How would we be able to find the point of inflection? Well, remember at point of inflection, the second derivative equals to 0. At point of inflection, second derivative equals to 0. Alright, so we have found the second derivative from, well, the second derivative of x equals to, we'll have worked it out to be 6x plus 12. Right, from the last page we have done that, and we're going to set it equal to 0. We solve for x. 6x equals to negative 12, therefore x equals to negative 2. But remember, we still have to check, because we need to check both sides of x equals to negative 2. So when you have a number a little bit less than negative 2, and when you have a number a little bit greater than negative 2, and see if the sign of the second derivative do change. So we're going to set up a little table like this. X and then f double dash x. So we have maybe so we have negative 2 in the middle. We can go negative 2.1, a little bit smaller than negative 2, and negative 1.9. All right. We know at this point it is at 0. Then we are going to sub in 6 times negative 2.1 plus 12. All right, and let's see what that number is. Well, 6 times negative 2.1 would be a number, would be 12.6, right? Negative 12.6 plus 12, we are going to have a number less than 0. So we're going to have a negative number. What about for the second derivative? So what about if I have x equals to 1.9 now? So 6 times negative 1.9 plus 12. 6 times negative 1.9, I would get a number less than 12 plus 12. All right, which means the answer is going to be greater than 0. So we can see at this point, it is when it's less than 0, I've got concaving down. At here, I'm concaving up. Here I have 0, which means the signs change. The signs of the second derivative change at x equals to negative 2. Therefore, at x equal to negative 2, it is a point of inflection. Inflection at x equals to negative 2. Alright, so I need to know what y is at that point. So we're going to sub in. We still need to know the y coordinates. So f negative 2 equals to negative 2 cubed plus 6 times negative 2 squared plus 9 times negative 2. And if you put it in, if you do it properly, you're going to get negative 2. Therefore, point of inflection at negative 2, negative 2. Alright, so now we have all the important information that we need. We have found the maximum turning point, right? We have found the minimum turning point, and we have found the point of inflection. And from the previous slide, we also have found the x-intercept and the y-intercept. We should be able to draw our graph. On the next page, I'm going to show you how to draw it. Okay, so let's put all those important information on a graph. We are on to the last step. What have we found? Well, we know the y-intercept is at 0, 0. We know the x-intercept is at negative 3, 0, and 0, 0, which is the same as the y-intercept. From the previous slide, we have worked all that out. We also have worked out the maximum turning point is at negative 3, 0, and we also have worked out a minimum turning point at negative 1, negative 4. We also have worked out the point of inflection. The point of inflection is at negative 2, negative 2. So let's plot it on a graph and see what it should look like. I apologize in advance that this graph might not look very nice because I'm using the drawing pad and I'm not very good at it yet. So 3, 4, 5, 1. No, that's not good. 1, 2, 3. I just want to use it to illustrate how we do it, but in exam, obviously you have to use some sort of a ruler, or your scaling must be a bit better. X and Y. All right, now let's plot our pretty graph. So y-intercept is at 0, 0, so we know it's going to cross the point, cross it here, 0, 0. And we know the other x-intercept is a -3, 0, so it's going to cross here. But we know this point is also the maximum turning point, so the curve is going to look like this at this point. Right, it's going to be curving down, concaving down. We also know the minimum turning point is at -1, -4. -1, -4 is around there. And we know at this point it's going to be concaving up at this point. Okay, let me just try it a bit better. So at this point, at -1, -4, it's going to look like this. So we do have enough information for us to join up our graph. But the last thing we know is at the point of inflection, -2, to at this point, this is the point of inflection. So this is where the concavity change. So here it's going to be concaving down, but as soon as it crosses this point, then it would be concaving up. And just connecting the dots, it's gonna go across. Alright, this is really pathetic, this graph. But that's how the graph should look like. Okay? And you would want to label the important points. 0, 0, and this would be 2, -2, -2, and this would be -1, -4. And label your graph. This graph would be y equals to x cubed plus 6x squared plus 9x. See, you don't even need a graphics calculator to plot this graph when you can go through this analysis, right? You can use second derivative and first derivative for you to identify the important points. Then you can draw this pretty graph. And if you want to, or if you've got time, maybe you can say this is the maximum turning point, this is the minimum turning point, this is the point of inflection, and x-intercept, y-intercept. That's how you do it. It's not hard, but it is a time-consuming process. But all we're doing is following the process. We're linking a few ideas together. But once you can do that, it won't be too difficult to draw, to put a graph together. All right, so now let's see if this question is in the calculator part of the exam. What would you do if they ask you to sketch this graph and determining all the other important critical points and the nature? What would you do if you need to use a graphics calculator to solve this problem? Chances are, if this question is in the calculator part of the exam, you will be given much less time to do it. All right, so you need to be very familiar with how you use your calculator. All right, so you're going to work along with me. So don't just be watching this part of the video. I want you to take your calculator out and actually pressing those buttons and make sure you're looking at the same thing as I do. Okay, so let's plot this on a graphics calculator. You should be familiar with how to plot a graph on graphics calculator. It would be on this button, the y equals to button on the top left corner. Let's just type it in. We want to plot x to the power of 3 plus 6x squared plus 9x. Enter. All right, so y1 is saved. with this function, just press graph. Alright, so now this is my pretty graph. You might want to play with the zoom to just make the window a little bit zoomed in so you can analyze a little bit better. Maybe I will go from -5 to probably 3, and well, because you know it's just going to keep going up, this is just going to keep going down, so I don't need that much for y. So let's just adjust the windows a little bit better. Let's just, maybe I will go from -5, I don't want the last, to maybe 4, and then for my y I want to go from -5 to, let's say, 4. Doesn't really matter. I just want to have a better, sorry, I must have typed something wrong. Yep, -5, not 50. It happens all the time. Alright, so now let's look at our graph. What do we need to identify on this graph? Well, first thing first, we need to find the x-intercepts and the y-intercepts. How do we find that? On this graph, you can see it should be at this point and it should be at this point. But you can ask the calculator to solve it for you. This is an important bit. How do you do that? You go to second and count. Alright, and now you're looking at the 0. Right, 0 is another word for x-intercepts. So we'll go to 0. Alright, so let's say I want to find the coordinate of the point that I'm pointing at with my mouse cursor. Alright, this bit. Well, yeah, you can see 0, 0, but I want to verify on my calculator. I want the calculator to tell me a value. So the first question they will ask you is the left bound. What this is saying is it wants you to move the cursor to the left of that point. So I'm just going to move it to the left of that point. It doesn't have to be exactly, it can be around here. Okay, this point, this x is at the left of the point that I want the calculator to tell me the coordinate for. So, okay, now I'm at the left of that point. I press enter. The calculator will ask you the right bound. It wants you to move this x to a point right of the point that you want. So I'm just going to move it to the right of the point and press enter. Okay, and then it wants you to guess. So what you're going to do is you're going to move this cross to the point as close as possible to the point that you want it to calculate for. So it looks like, well, the resolution is not that great, so it looks about there. Then I press enter. Then the calculator will give you the coordinate of the 0, which is at 0, 0. All right. Let's do the same thing for this bit. All right. Let's see how we can get the calculator to tell me the coordinate of this guy. You go to second. Right. Count again. We want to find the 0. First, it will ask me for the left bound, so I'm just going to move this to the left of the point, to the right of the point, right bound, and guess what the point is. It's around there. Okay, so the coordinate would be -3 and 0. Don't worry about the 0, 0, that 0, 0, 0, 0, 0, 1, because the calculator is doing a bit of approximation at the background, so it's not giving you the exact value, but you would know, you can safely assume that this is -3 and 0. All right, so now we've got the intercepts done. Let's see what we can do with the stationary points. So now let's see how we can find the stationary points using our graphics calculator. Remember, at the stationary point, what are the features of stationary point? Or at the stationary point, your first derivative, right, dy dx, should be a 0. At those points, it should be at 0 gradient. So looking at the graph, you can safely assume that it should be around here and around here. Let's just be sure with our calculator. This is a really, really cool function. If you go to plot the graphics calculator can actually plot the derivative function for you. So go to y. Alright, so now I want to plot another one. So I go down to y2 and you go to mass. Then we're going to choose number 8 and derive. So I go 8. I want to differentiate a function with respect to x. So I put x down here. Then here, you have two choices. You can type this whole thing in. You can type x cubed plus 6x blah. Or you can go to vars and go to y vars, go right, and choose the function. Go number 1 function, and I want to find the derivative function of y1. So I'm going to choose y1. Alright, so now I'm differentiating y1, which is this guy, with respect to x. And you have to enter one more parameter. It's asking you which value of x do you want it to differentiate for, and you would put x because I want all the value for x. Press enter. Now you hit graph. Okay, so now you can see the red line is the derivative function. Alright, the red line is the derivative function. So you can see it is a quadratic function, and you can see where at the function, at the derivative function, would the derivative function be 0, right? So these would be at the 0 at the x-intercepts. So by finding the x-intercept of the red curve, you should be able to find the point that the derivative function equal to 0, right? And then you can use those points to work out the stationary point of the original function. Okay, so it looks like it's a 0 here, it's a 0 here. Let's use our graphics calculator, the count function, to help us to find the exact point. Second, count. So again, we want to find the 0. It is, at the moment, it is on the first curve. So I'm going to hit the up button to move it to this curve. So let us find the 0 for this point first. So I'm going to move it to the left of that point. Okay, it's at this point. Press enter, and the right bound of this point, press enter. Guess will be around there. Okay, so we know the first stationary, well, it would be at x equals to -3. All right, let's find the x coordinate for this point as well. Second and count. Go to 0. I would make sure I'm looking at the red function. Okay, I'll go to the left of the point and the right of the point and have a guess. It looks like it's around there. So it would be at x equals to -3 and x equals to -1. So these two are the points when the gradient equals to 0. So I know the x coordinates of the point. I now also want to find the y coordinates of that point. So you can use a really cool function. Go to second, count, and we can go to look for the value, right? At x equals to -3, so you just type in -3. And for the original function, y equal to 0. So we know one of the stationary points is -3 and 0, right? Which you should be able to read off from the graph anyway. And the other one would be at, so the other one would be this guy. So again, I go to second count. I want to find the value of y when x equals to -1. Press enter. There will be -1 and 4. -1 and 4. Okay. All right. Looking at this graph, you can easily see that this is a local maximum and this is a local minimum. How can we verify it? Well, we have to use the second derivative to verify it. Next slide, I'm going to show you how to do that. And also, I'm going to show you how to use second derivative to work out the point of inflection. Okay, so now let's involve our second derivative to help us to solve this problem. How do we derive this for the second derivative? Well, you go to y. Now I'm going to have another function. I'm going to have y3. Again, go to mass and derive. So number 8. I'm going to be differentiating with respect to x. This time I want to differentiate y2. So I go to vars, y vars function, and y2. And I also type in x here, which I'm going to go graph, and then I should be able to see the second derivative function. Okay, so the black line is the second derivative function. All right, what can we use it for? What can we use it for? All right, remember the second derivative. What does the second derivative tell us? Well, second derivative, or y double dash, it tells us the concavity, right? So let's look at our first stationary point at here. Remember the blue line is our original function. At this point, obviously the second derivative function is at negative, right? Obviously it's right down here. So at this point, at -3, 0, y dash dash would be less than 0. What does that mean? Well, remember, if the second derivative is less than 0, it means it's concave down. All right, which is justified looking at the curve, right? All right, let's look at the other stationary point, this guy down here. What about at -1, -4? At -1, what is our second derivative? Remember, the second derivative is the black line, it's right up there, which means our second derivative is at positive, is greater than 0. If it's greater than 0, it means it's concave up, right? Okay, so which also justify what we're seeing here. If we are looking at this point at 3, 0, if it's concaving down, it must mean that this is a local maximum, right? You're right, local max. Likewise, looking at -1, -4, it is concaving up. Looking at the shape, it has to be a local min, which we have shown that you can use the second derivative to justify our answer. Now let's use our second derivative to find our point of inflection. Remember, at the point of inflection, okay, at point of inflection, what does the point of inflection show us? Right, at the point of inflection, the second derivative would be 0, right? And the sign would change at the right and at the left of the, and also sign change left to right of this point. So looking at our second derivative function, you can see this is the point when the second derivative equals 0, right? And the left of slightly smaller than this point, we are at negative. Slightly greater than this point, we are positive. So we can see from the second derivative graph, we can see point of inflection would be at x equals 2. Well, looks like this is a -2, but let's just check just in case. So again, we're going to go to second, go to count, and we want to find the 0. This time we're looking at the second derivative function. Okay, we're going to y3. Left bound, so I'm going to move the cursor to the left of the function, which is here. Right of the function, which is here. Have a guess where it is. It looks like it's here. So the point of inflection would be at x equals to -2, which corresponds to a point down here at the original function. We are nearly there, but we still need the y value for the point of inflection. So y value for point of inflection. How do we do that? Very simple. Second count. We want to calculate the value when x equals to -2. Sorry, that was a minus. So -2. Go enter. And the y value is -2. So we know, therefore, point of inflection at x equals to -2, y equals to -2. And you can use it to check, because you can see at this point, at the left of this point, your curve is concaving down. And at the right of the curve, your curve width is concaving up. At this point, so this is the point where the concavity of the curve changes. So I have shown you a lot in today's lesson, or maybe you could do this lesson over 2 days. But the key point that you need to know is you need to be able to be familiar with 2 methods. One with your calculator, the other one without your calculator. The theory is the same. However, the key is if you are in a non-calculator exam, you just need to work everything out yourself. But if it's in a calculator exam, you probably will be given less time to do this question, but you need to know all these theory before. So you need to know, okay, all right, the first derivative tells me the gradient at each point of the graph. So I can use the first derivative function to find the stationary point. And then I can use the second derivative function to find the point of inflection. I can use the second derivative function to help me to check the concavity of different points of the graph. All right, so we're still using the same theory, but the method of working out is different. And also, even if it's in a calculator exam, you still need to articulate what you're doing. Write down your steps. Let your marker know what you're doing. Don't just draw a graph and say, here you go. No, they want to see your thought process. All right, they don't need to see you actually differentiating the function. You see, when I was using the calculator to work out these functions, I didn't do any differentiation myself. Right? I didn't do any numerical calculations myself. You don't need to waste time to write out those steps, but you need to explain to the markers how you got the final answer. How did you know -2 is the point of inflection? Right? Explain the theory behind your answer. Okay? Practice, practice, practice. You need to be very familiar with your graphics calculator. That's why I've been saying all along, use it all the time. Don't use decimals. Don't use other things because you can't bring those other things into your calculator. Use your graphics calculator. Make it your best friend. Alright, so let's do another one. We're going to do another sketch. This time we're going to sketch a quartic function. Again, we're going to do this without a graphics calculator. So we're just going to be sketching this graph using our analysis of first and second derivative. Very important example. If you're feeling confident, go into it yourself, pause the video. However, we can all do this together. The question is asking you for the axis intercepts, x and y intercepts, stationary point, and the nature, and also it wants to know if there are any points of inflection. Alright, so nothing that we are doing here would be new, but I'm just going to illustrate the process again, so that you're familiar with what we need to do here. All right, let's get into it. X-intercepts, x and y-intercepts, easiest to find. Let's find the y-intercepts first. Y-intercept occurs when x equal to 0. In this case, if x equal to 0, y equal to 0, because we just sub in x as 0. Therefore, the y-intercept is at 0, 0. Let's solve our x-intercepts. X-intercepts occurs when y equals to 0. So we're going to set x to the power 4, take away 4x cubed equal to 0, and we need to solve for x. How do we solve it? Well, the easiest one we can see would be x would be 0, but the other one, well, we need to factorize first. What is the common factor between these two terms? It will be x cubed, take away 4 equal to 0, therefore x equals to 0 or and 4. So therefore x-intercepts would be at 0, 0 and 4, 0. Easy enough. Alright, so now we're going into the stationary points. Where do we find the stationary point? Stationary points occurs when the first derivative equals to 0, right? Stationary points are the point that it has got 0 gradient when y dash equal to 0. Okay, and the question is also asking for the nature of the stationary points, which means we need to know whether it's a maximum, minimum, or a point of inflection. So we need the second derivative to help us out as well. So let us differentiate the function to find the first derivative, and then we also want to find the second derivative. Okay, so first derivative would be, well, just simple differentiation for x cubed, take 12x squared, and then the second derivative would be 12x squared, take away 24x. Okay, so these two are the important functions that we can use later on to help us out. Alright, so now I want to find the stationary point. Stationary points, again, we know that stationary point, first derivative equals to 0. So we're going to set y dash equals to 4x cubed, take 13x squared. We're going to make that equal to 0. Alright, and then we're going to solve for x. How do we solve for x? Well, we first factorize, right? Take out the common factor. 4x squared would be the common factor. That becomes 4x take 3 equals to 0. If you solve for x, in this case, x would be 0 and 3. Okay? So let's check. So now we know the stationary points occur when x equal to 0 and 3. But we need to determine what sort of stationary points are these. Alright? So at x equal to 3, let's see what it is. So at x equal to 3, we are going to use y double dash, sub in y double dash for 3, and we look at whether or not it's a positive or a negative. Then we can use it to decide whether or not this is a, I don't know, a max or min or a point of inflection. Alright, so let's sub it in. It will be 12 times 3 squared, take away 24 times 3 equals to 36. Right? 36 is a positive number, which means it is concaving up. Okay, you need to remember these by now. Okay, if your second derivative is greater than 0, it's concaving up, which means this is going to be a minimum turning point. We also need to find the y coordinate. How do we find the y coordinate? We sub in x equals to 3 to the original equation. So we're going to put in, sorry, that was bad. we're going to put in y equals to 3 to the power 4. Take away 4 times 3 to the power of 3. And your answer should be 4 times 4, 3. Okay, so that should equal to negative 27. Therefore, 3, negative 27 is a minimum turning point. Alright, so we found one of the points. Next, we are going to look at when x equal to 0. Remember, we have identified another stationary point occurring when x equal to 0. So we need to check what sort of turning point is it. Alright, so let's look at when x equal to 0. So when x equal to 0, well, we want to check what sort of turning point it is, so we need the second derivative. We have worked out from the previous page that the second derivative, the function was 12x squared, take 24x. So we're going to sub it in for x, which is 0, take 0, which equal to 0. So at this point, we can see that the second derivative is at 0. So this could possibly, be a point of inflection. But you see why I put a question mark there? Because I haven't really checked. I can't confirm whether or not it is a point of inflection yet. So we need to check. How do we check? We use the second derivative to check. And then we look at 2 points slightly greater and smaller than that point. So when x equal to 0, and then we'll check what y double dash is. So let's go negative 0.1 and then 0.1. What we do here is we sub in 0.1 into the second derivative function. So 12 times negative 0.1 square, take away 24 times negative 0.1. Okay, so we need to calculate whether or not this is positive or negative. We don't really care the actual number. We just need to know whether or not it's positive or negative. Well, so if you look at this bit, the negative 0.1 square, it will become, this will be a positive number. Take away 24 times negative 0.1, that will also be a positive number. So obviously the answer is going to be positive. I don't care what the actual number is. I just want to know the sign. All right. Well, at 0, we know the second derivative is 0. So let's check at 0.1. So 12 times 0.1 square, take away 24 times 0.1. Okay, so have a little think about whether or not the answer is going to be positive or negative. Well, 0.1 square is going to become, so you can see 0.1 square is going to be 0.01 times 12, then you're going to have 0.12, and then you take away 24 times 0.1, which is 2.4, then we know the answer is going to be negative. You've got a smaller number taking away a bigger number, so you know the answer is going to be negative. All right, so what have we seen here? We can see the sign did change, right? We've got the second derivative greater than 0, which means the sign of the second derivative is greater than 0 is positive, which means it's concaving up at this point. And here I've got no gradient, 0 gradient, and here I will be concaving down. All right, so you can see the sign did change, or you can write a note. The second derivative has changed from concave up to down. Okay, so there is a stationary point of inflection at 0, 0. Okay? Alright, that's how you work it out. How do I get the other 0? Because I know. How do I know the y coordinate of this point is 0? Because I know 0, 0 is the x-intercept. So we have already worked that out. Otherwise, you could just sub the x value into the original equation to find what's the y coordinate. But because we know it's going to be 0. Now we're going to look at whether or not if there are any other points of inflection. So let's see if there are other points of inflection. We know we have already found all the stationary points, but there could be some points of inflection with which are not stationary, right? They won't have 0 gradients, but they are still points of inflection. How do we find the points of inflection? What do we use? Well, we use the second derivative, right? What happened at the point of inflection? Second derivative equal to 0 at points of inflection, right? So we're going to set the second derivative equal to 0. Second derivative is 12x squared, take 24x. We're going to set it equaling 0. How do we solve it? Factorize again. 12x, take it outside of bracket, take 2 equal to 0. So x equal to 0 and 2. We have already talked about this one. We have already done. Right, that's the 0, 0 point of inflection. So we have to check what happens at this guy. Alright, so we have to check what happens at this guy. So let's do that check quickly. Again, we set up a little table. X and then y double dash. 2. We'll do 2.1 and then we can do 1.9. Slightly greater and smaller than that actual point. We sub in y double dash for 1.9, so it will be 12 times 1.9 squared, take away 24 times 1.9, and we know if you do the math properly, it is going to be less than 0. It's going to be less than 0. And at 2, we know it's 0. And then if we do the same check for 2.1, we know the second derivative is going to appear as greater than 0. So you can see this check shows that it is in fact a point of inflection because we are going from concaving down to concaving up. So therefore at well, this is a point of inflection. At x equals to 2, it is a point of inflection. Point of inflection. We also need to find the y coordinate of that point. So the y coordinate of that point would be, well, we sub in x equals to 2 into the original equation, which is, well, 2 to the power 4, take away 4 times 2 to the power 3, you should get negative 16. So therefore, point of inflection at 2, negative 16. Alright, so now we have everything that we need. All we need to do is to plot them all on a graph. We'll do it on the next page. Okay, so let's summarize what we have found on this page and then we're going to plot the graph. Well, we have found that x and y intercepts are the same point, is at 0, 0, and we also found at that point it is actually a stationary point of inflection. Okay, and that's at 0, 0. So at this point, 0 gradient, but concavity change. We also have found another point of inflection. Point of inflection is at 2 and negative 16. Alright, that's our other point of inflection, but this one is not a stationary point of inflection. We have also found the other x-intercept at 4, 0. Okay, that's the first thing that we've done for this question. We have also found the minimum turning point at 3, -27. Alright, so let's plot a pretty graph. These are the 4 points that we need to show on our graph. As I would apologize in advance that it won't look that nice because I'm really not good with this writing pad. Okay. Since we've got some big numbers, we might not go up by 1, we might go up by, let's say, 10. 10, 20, and then we go down to -30. Okay, I'm sorry for my really pathetic drawing of a graph, but I care about the process a little bit more than the prettiness of this graph. However, in your exam, you can't draw like that. Alright, let's plot this graph. Okay, the first one we know it is our stationary point at 0, 0. This is our xy intercept and also the point of inflection. We know the concavity would change. Go back to our table before, we can see that the concavity would change from concaving up to concaving down. So we know that it should look like this, and then it's going down like that. So it's from concaving up to concaving down at this point. What else do we know? We know at 2, -16, so this is 2 and -16 is around there. This is another point of inflection. Okay, so we're doing this point now. It is going from concaving down to concaving up. So it's concaving down, and then it will be concaving up from here. And then let's plot our minimum turning points. 3, -27. So that's 3. -27 is about there. So we know at this point is going to change the direction of the curve. So it will be concaving up, but it would be going from decreasing to increasing like this. And finally, we know the other x-intercept is 4, 0. So this is where our line is going to cross. Okay, this is a very pathetic drawing, but let me just draw it a little bit better. And we know it's going to be concaving up, and it is going to cross the x-intercept and continue to go up. So this is our drawing. Alright, label our graph. Y equals to x to the power of 4. Take away 4x to the power of 3. And we are done. Right, we can see we have labeled all the important points. This is my point of inflection. This is another point of inflection. This is the local minimum. This is my x-intercept. This is also the x and y intercept. Okay, so all the important points are labeled. Alright, let's do a quick follow-up question on stating the value of x where the function is decreasing and where the function is concave up. To do that, we probably need our graph again, so I'm just going to bring the pretty graph here. Let's do part 1 first. Part 1 is asking you for the values of x where the function is decreasing. So you can see this bit is decreasing, right? And also from here to here is decreasing. But at 0, at x equal to 0, the function is neither increasing or decreasing, because at 0, it's a point of inflection. It's a stationary point of inflection. So the gradient is at 0. So to answer that question, you should only be considering this bit except 0, and also starting from 0 down to this bit. Alright, so what you should write for part A should be, or for part 1, would be the function is decreasing when x is less than 0, or x is greater than 0 but less than 3. So for this bit. Okay. Alright, part 2, let's look at where the function is concave up. Well, concave up, you should be able to see between here, right? This is concaving any before x equal to 0, this is concave up. Right? Concave up means it goes like that. So this bit is concave up. This bit is concaving down. But between here and keeps going is also concave up. There's no more points of inflection. Remember, the concavity only changes at points of inflection. This bit, concave up. This is a point of inflection, so it becomes this concaving down. This is another point of inflection, is concaving up. There's no more points of inflection after that. So this is all concave up. So what you should write for this bit would be, for part 2, the function is concave up when x is less than 0, which is this bit, and also from the point of inflection and onwards, or when x is greater than 2. Alright, that's how you do it. So you see, we have solved a problem completely without using your graphics calculator. Alright, so now you're going to do this same question again, but you're going to use your graphics calculator. Alright, you're not just pressing them. I still want you to write down your working out, and you need to include all the critical points. Okay, another question for you to do. Use both methods as well. The first time you do it without a calculator, the second time you do it using your calculator. See if you can use your calculator to verify your answers from without using the calculator. The answers would be on the next page. I'm not going to go through it. I've talked enough for this lesson. It's your turn now. Alright, so these are the relevant textbook sections and the exercises for the topic. I want you to read through the textbook examples and then do some of the exercises. Obviously, you might not have enough time to go through all 3 textbooks. Choose the harder ones to do once you have managed the simpler ones. 2 hours of maths per day minimum. Again, do as much as possible. Don't go easy on yourselves. The competition is still on. Work hard, practice, practice, practice. Alright, good luck, have fun.